All right, so thank you everyone for joining. Today's speaker is Doga Ostork, and she received a PhD in space physics and a conjugate PhD in scientific computing from the University of Michigan in 2018. And her PhD thesis focused on understanding solar wind dynamic pressure control of the coupled magnetosphere-ionosphere thermosphere system using MHD modeling. After graduating, she joined NASA JPL as a postdoc in the ionospheric atmospheric remote sensing group. And while there, she developed the high latitude input per mesoscale electrodynamics framework, a code library that enables incorporating measurements of electric fields as boundary conditions to general circulation models. And in 2020, she joined the Geophysical Institute at University of Alaska Fairbanks and has been working as a research assistant professor there since then. And her research interests are magnetosphere, ionosphere, thermosphere coupling, interhemispheric asymmetry, mesoscale variability in the near-Earth environment, and application of machine learning to heliophysics, data, and citizen science. And today she will present on the new insights into the dynamic auroral phenomena. So please go ahead.
Thank you so much. Hello, good afternoon, and thank you so much again for having me present the High Altitude Observatory Colloquium today. Um, Doğa Öztürk, I work at the University of Alaska Fairbanks, and my talk today is going to be on the new insights into dynamic auroral phenomena. So when somebody visits Alaska, the first question they ask is when they can see the aurora. And as you can see, there are various tools and companies that claims to guarantee seeing the aurora. But needless to say, they don't always get good reviews in their websites because when we talk about seeing or aurora tourism, people want to see really bright dynamic features, right? So our understanding of these dynamic bright features, dynamic aurora, is very limited, let alone our ability to forecast them. So that's why today I want to talk to you about what particularly dynamic aurora is and why our forecasting efforts do not always hold. So this is the outline of my talk. I'm going to first talk about the aurora in general and in particular dynamic aurora, or as known as mesoscale aurora. And then I will talk about some of the new tools that have been developed at Alaska, at University of Alaska, or at different institutes that help us understand dynamic auroral phenomena better. So very briefly, aurora starts with the solar activity. We have the constant stream of particles coming from the sun in terms of solar wind or coronal mass ejections or solar flares that emits these charged particles into the interplanetary magnetic field. Then what happens is these charged particles, when they're in the vicinity of Earth, they start traveling along the magnetic field lines and they are scattered into the Earth's upper atmosphere if they have a certain level of energy, which is the atmospheric, which is the particle precipitation. When they are precipitating, these charged particles collide with neutral molecules at the Earth's upper atmosphere, which then causes them to emit photons. And based on the altitude range or the constituents that they are colliding with, the aurora has different colors. So here's how that altitude variability looks like. So at the upper edge of aurora, which is around 250 kilometers, we have the red aurora, which is due to the oxygen atoms. Between 200 to 150, we have green aurora dominating the general auroral displays. This is due to the oxygen atom. And at the lower edge of aurora, which is around 80 to 100 kilometers, we have the nitrogen molecules that kind of emits purple light. So aurora is imminently related to geomagnetic activity, since charged particles are constantly emitted from the magnetosphere, forming the auroral oval. This auroral oval, as you can see here through the Dynamics Explorer images, first appears as a quiet, very dim oval type shape. In time, we can see it getting brighter and that it starts expanding, becoming more active. At times, it appears patchy, and then with respect to magnetic local time, we can see that this auroral oval also shows variability. It takes around 3 to 4 hours for this whole process from this dim to go to the more active bright and then to patchy, and the basically electrode jets associated with this aurora to subside. This has a periodic basically cycle type behavior, which is known as the auroral substorm, and this has more or less the same periodicity with magnetospheric convection. So magnetospheric convection, or what we know Danji cycle, is also associated with the geomagnetic substorms. We can break down the aurora into two main physical processes here. One of them is basically the convection, magnetospheric convection, and it is ionospheric food point, the ionospheric convection, or the electric field and velocity. And the second is the particle precipitation, basically the flux and energy and the location of where the charged particles are mostly emitted. So here we can see the three different phases of the geomagnetic substorm: the growth phase, where the plasma sheet is thin, the expansion phase, where the near-Earth neutral line forms, and the recovery phase, where the plasmoid is further released away from the Earth, and the Earth's magnetic field becomes dipolar again. So for each of these magnetospheric convection, we can see that the kind of the corresponding auroral substorm image, you can see that this growth phase corresponds to increased magnetic flux and the initial brightening. The expansion phase maps to the patchy type of the patchy portion of the auroral substorm, and the recovery phase where the auroral starts to dim again and the flows and electrode jet subsides. Here is an animation basically showing what we just discussed in 2D, the reconnection and the particles being energized along the field lines and precipitating into the upper atmosphere. So the geomagnetic substorm and storm are widely studied phenomena. We can tell when they are most likely to occur. So for example, the conditions at the sun can indicate when we might have geomagnetic storms, substorms. When we have sunspot number increasing, we know that we are propagating towards a solar maximum, which means that there's more likelihood of getting the coronal mass ejections or solar flares, which then can tell us that this is basically a time interval that we are more likely to see geomagnetic storms. And again, the solar wind and IMF interplanetary magnetic field conditions could also indicate whether we will have geomagnetic storms or substorms based on whether the solar wind is flowing fast, which means that the dynamic pressure of the solar wind will increase and it will cause magnetospheric compression, or prolonged periods of negative Z component of the interplanetary magnetic field, which means that the dayside magnetic flux will be eroded and will be loaded to the magnetotail, which will create most likely geomagnetic substorms. NOAA and NASA provide regular space weather forecasts where we expect these conditions to change over time. You can see the there's the solar flare monitor, auroral oval again, or the solar wind engine model, which shows basically how the conditions might be changing in the future. So again, based on all these inferences that we have, we can also predict how the statistical behavior of the system is going to behave like based on years of observations. Again, we broke down the aurora into two components, the convection and particle precipitation earlier. So we have statistical models to describe the convection in the ionosphere. One of the most widely used ones is the Weimar model. This depends on the Dynamics Explorer drift meter measurements, and they are binned for different solar wind and IMF conditions and geographical locations. There are also very other successful models that describe the large-scale precipitation. Here you can see the Weimar model, the ionospheric potentials, and the basic pathways for ionospheric convection. This also helps us understand how the electric field is going to be like in a large-scale global sense. For particle precipitation, we have models like Ovation Prime, which are based on particle measurements from DMSP satellite or similarly hemispheric power indexes. So these particle data is also binned for different solar wind and IMF conditions and geographical locations to describe the number, flux, energy, and basically the locations that we are going to see the increases based on expected activity. So how does expectation fare with reality? You can see from here a SWIPC Aurora forecast that shows us the aurora, and this displays the probability of seeing aurora. So the color as it goes to green to red, we are hoping to see higher probability of observing aurora at a given location. So these observations are produced in a quasi-static sense. So when we say large scale, this is what we mean. But when you look at Thames all-sky imager mosaics here, you can see there are lots of different structures. For example, you can see more thin arc-like structures. You can see propagation towards the east, the west. You can see north-south aligned brightenings propagating. So basically, there's much more structures going on. So this is the dynamic type of aurora that we referred to in the beginning of this talk. So these are not, we are not able to forecast these dynamic features because they are very different. There are various different types of physical processes that lead to aurora. This is just a subset of existing auroras. You can see the auroral arc here, which is like a very thinnish type of line that appears very bright. You can see the pulsating aurora. This is not as bright, but you can see that it kind of has that periodic, basically the dimming and brightening happening. We have the torch aurora that is from south to north elongation that you can see distinctly. There's spiral aurora, omega aurora that is similar to torch aurora. There's the string of pearls or auroral beads, the black aurora, which appears as the reduction in the flux, and the steve, which recently joined the aurora family. So in order to understand why or how, basically, or when the aurora is going to happen, we have to have a better understanding of how these mesoscale auroral forms relate to different magnetospheric processes. When we talk about different types of aurora, or basically the most common categorization, it's not based on the scale size, but it is based on the basically the brightness of the aurora. So we can look at two different categories: the diffuse aurora, which is particles scattered into the lost cone. This can include wave-particle interactions, but there is no further acceleration of the particles when we say diffuse aurora. That's why structures that appear dimmer in all-sky imagers are classified as diffuse aurora. The discrete aurora has an additional acceleration between the upward field-aligned currents and due to the potential drop between the magnetosphere and ionosphere. That's why the discrete aurora has this energized particles, which then results in them appearing brighter. And there is the pulsating aurora, which is a type of diffuse aurora. As we have seen, these are irregular quasi-periodic patches of diffuse aurora. So when we look at the auroral oval, you can see that there is a distinction between the discrete and diffuse aurora based on the latitude that this basically the magnetic field lines map to in the magnetotail. So towards the northern end of the auroral oval, we see the discrete auroral features, and towards the equatorward boundary, we see more of the diffuse aurora features. You can see the pulsating aurora is located along the equatorward boundary, and it can form these omega-type bands, which also appear dim to eye. Or in the discrete aurora, we have auroral streamers, poleward boundary intensifications, and again, the bead-type structures forming. So following the review of Colin Forsyth that was published in 2020, some of the most commonly seen mesoscale auroral types are identified as these poleward boundary intensifications, auroral streamers, omega bands, beads, and giant undulations. As for poleward boundary intensifications, we see that on the poleward boundary of the auroral oval is really localized bright features. So they are transient, and basically they are reported in all levels of geomagnetic activity. They can be reported in the expansion phase, main phase, or recovery phase. And these are generally considered to be manifestations of processes related to magnetotail reconnection. There are three different classes of poleward boundary intensifications. depending on their alignment and propagation directions. So whether they are in the north-south aligned or east-west aligned, they can be classified separately because of processes associated with their convection in the magnetotail. And then how the polar boundary intensifications occur, what are their origins, and how they're associated with new auroral arcs through their alignments is still an open question. The second type of mesoscale structures or dynamic auroras are the auroral streamers. So here you can see the polar ultraviolet imager. Basically, the auroral streamers are most commonly observed that elongated from north to south directions, but they can also be east to west aligned. Here, what we are looking at is a north to south aligned auroral streamer. And there were three spacecraft basically at this time that were observing these auroral streamer. Here with interval, you can see two injection and dispersion signature through protons for this auroral streamer. Here is the observations from geotail showing the velocity, magnetic field, and the pressure. You can see that the velocity is in the first one increased slightly, but there's a significant increase in the second observation of the auroral streamer, and a lot of fluctuations in the magnetic field strength and a drop in the pressure. And the last one is the Lennon spacecraft, which is closer to the Earth. It's in the geosynchronous orbit at this time, and it records an enhancement. Again, it's hard to see the first one, but around basically 8 minutes later than the geotail, it records these enhancement at different energy levels. So these auroral streamers are mostly associated with bursty bulk flows that are propagating towards the Earth from the magnetotail, mostly following a magnetotail reconnection type event. And they can also create large, really localized magnetic perturbations associated, tracing the auroral streamers in the ground magnetometer signatures. And their life cycle in relation to the magnetotail transient events is also still an open question. The third type of dynamic aurora that I want to talk about is the omega beads. They are basically, if you can follow my mouse, they are inverse or like reversed omega shapes, as you can see. They have three different types. So this one is the O type, the classical omega band. Here you can see two of them next to each other. So what happens is that during their where they join, these two omega bands form a torch, basically a north-south aligned brightening. This is called the T-type omega bands. And when there is a lot of activity and these eastward propagating features could appear as the OT type. Basically, both omega and torch is very evident in the all-sky imager signatures. So these omega bands are mostly observed propagating eastward, and they are thought to be associated with the downward auroral polarization streams that are recently described by Liu. When there are poleward extending features, as we said, they're called torches, and these are basically showing a sequence of here upward and downward field aligned current systems. And again, these are mostly observed in the recovery phase, and here basically the type of the currents and the way that these structures are formed indicates there's significant shear type motion associated with these type of aurora. So they're thought to be associated with Kelvin-Helmholtz or vortex-like structures in the magnetosphere. And the last type of mesoscale aurora that I want to talk about is the auroral beads or the string of pearl formation aurora. These are spatially periodic auroral forms, mostly in the azimuthal direction. You can see that they are brighter. So as opposed to the omega aurora, these are thought to be discrete aurora types, and they have near simultaneous exponential growth in their brightness, which again supports that they are discrete forms. And this is associated with plasma instabilities like ballooning interstability or interchange instability. And it was thought that these type of aurora occurred before substorm onset, kind of like a indicator of a substorm onset. But recent study by Soratia et al. Showed that using gamma simulations, they were able to get really high resolution simulations with this MHD model. And what they have shown is that this ballooning and interchange type instabilities can occur basically at any point in a substorm cycle. So they're not only confined in the time interval prior to a substorm onset. So why we are really hoping to understand mesoscale structures? Because we have a system, the ionosphere thermosphere system, and our understanding of its energy budget is incomplete if we do not understand and try to find a way to model these mesoscale structures. Here you can see that the energy input to the IT system can be simply expressed with a form of Joule heating, where we have the Peterson conductance. Again, when we talked about Aurora, we said let's classify it into two distinct categories. One of them, let's try to explain it with particle precipitation and the convection. So you can see that that's why that component is very important. This is the particle precipitation related component that we were talking about. And then we have the electric field or the convection that we talked about. And we had a term that is the contribution from the neutral winds. So basically, if we try to express this system with the statistical model, we are going to miss out on a lot of the electric field variability. Here you can see a study that conducted by Weimer in 2005 electric potential model. Here are the Dynamics Explorer 2 ion-driven meter measurements shown with the blue line. This whole interval is only around 40 minutes long. And you can see that the red line shows the time-shifted estimates from the Weimer model. So you can see overall, the Weimer model does a very good job in capturing the large-scale behavior of the system. So you can see that it traces the directionality well, the mean average is captured well. But even over the span of a few minutes, there is so much variability that is measured with the Dynamics Explorer that is missed out by this statistical model. For example, here you can see almost 80 millivolt per meter. There's a difference between the red line and the blue line, indicating the missing variability. This directly goes into the equation. So that's why you can see how much of the energy that we will be missing out by not incorporating these mesoscale structures. So, and again, this energy, the Joule heating, directly goes into ion and neutral populations. It alters the density and the temperature profiles of the ionosphere and thermosphere system. Again, we would expect hazards in telecommunication. We would expect increased atmospheric drag. And again, as we talked about in the Auroral streamers too, these features can be associated with significant magnetic perturbations, meaning that they can create geomagnetically induced currents. As for the precipitation, particle precipitation part, here is the Fuller-Rowell and Evans model, which is a model that takes into hemispheric power index into account to come up with the Peterson conductance profiles, which is the sigma p component now. And here you can see the polar UVI measurements and the Peterson conductance inferred from them. As you can see, they can be very significantly different from each other. So while these empirical models describe the quasi-steady large-scale input, by lacking mesoscale variability, this where the energy is going to be inputted can also significantly vary. So here you can see that, for example, the energy, the sigma p, is very localized pre-midnight in the pre-midnight sector, as opposed to this almost very large oval type structure that we see. So this kind of leads to a lot of uncertainty in our modeling, especially general circulation models, because these immediately define our drivers for these systems. So this brings me to the new tools and missions, where I want to talk a little bit about data assimilation, machine learning, citizen science, education outreach, and missions that are in the works to understand this dynamic aurora better. First, I want to talk about the focal flat research range. We have an incoherent scatter radar called Pfizer at the Poker Flat, which has line of sight, which measures the line of sight velocities. And these velocities basically can be used to infer the 2D electric field estimates over the same region, or basically over an expanded region using different beam configurations. We can get up to 66 seconds temporal resolution and a spatial resolution around 0.05 degree in latitude and 0.3 degree in longitude, which is around 10 kilometers. So basically, this gives us a very good sampling rate to study mesoscale type of aurora or a mesoscale electric field structures. We have the Geophysical Institute magnetometer array, which helps us track different auroral features and the magnetic field variations associated with them. We have scanning Doppler images that measure the neutral wind and thermospheric temperature, which helps us infer how efficient the ion-neutral coupling could be when there is dynamic aurora. And we have the all-sky cameras across different regions like Poker Flat and Veneti that helps us also classify different types of aurora. So the first type of new insight is through the data assimilation or type of ingestion. The high latitude input for mesoscale electrodynamics framework that me and my colleagues developed helps us ingest these electric field estimates, the two-dimensional estimates from Poker Flat as drivers to general circulation models. So you can see that the EX and EY contour plots of the Poker Flat measurements at a given time. You can see it's located here, and the closer the radar, the more variability is observed because of the radar geometry. So basically, using a very simple finite interpolation scheme, we are able to calculate the potential differences in longitude and latitude, which can then be merged with any type of global specification of electric potential. And again, this doesn't have to be Pfizer. This framework can incorporate any estimate, theoretical calculation, or measurements like from SuperDARN into any type of global specification of a potential. You can see we regionally alter the potential fields, and there's a lot of filtering and smoothing involved to omit the boundary effects. But then we can basically run the general circulation models. Here we use the University of Michigan's global ionosphere thermosphere model with the HAO driven versus Weimer driven runs. Here you can see that the same EX and EY components for electric field over 1 hour, like 90 minutes basically. The black dotted lines show the Pfizer estimates for that particular electric field that we were trying to incorporate. The gray shaded regions show us the errors. Yellow lines show the Weimer-driven GITM results for the electric field, and the red lines show the HAO-driven GITM results. And as you can see, both of the variability and the magnitude is incorporated when we use look at the HAO-driven GITM results. And again, here, especially in the latitudinal component, you can see that up to there are certain times there are 40 millivolt per meter differences. And now we are able to incorporate them into our driving to further study how these mesoscale structures could be affecting the ionosphere thermosphere system. We also know that these kind of structures deposit energy locally, and looking at the altitude profile over Pfizer, we can see that there is an order of magnitude increase in energy transfer rate between the GITM that is driven with Weimer or HAO, and around 120 kilometers, it's around 140 nanowatts per meter cube. We also try to incorporate the local precipitation because, again, convection and the precipitation. So here you can see the beams and the electron density measurements along those beams using Pfizer. Here we are looking at Pfizer beam 6. Here you can see the configuration of these different beams, and the dashed line shows the Pfizer beam 6 electron density measurements. You can see there's significant fluctuation because this was nighttime. Sorry, that's why we had to kind of average its behavior. And then you can see the Weimar and ovation prime-driven GITM results at the same location. Especially below 225 kilometers, you can see there's significant difference between the simulated electron density using these large-scale drivers versus the actual measurements. So basically what we want to then incorporate is assume that the difference is due to the mesoscale precipitation. So we went back to the continuity equation and we tried to turn this into an optimization problem. So to minimize the difference between the simulated electron density and the measured electron density, we assume that this the difference is due to the auroral ionization that was lacking in the large-scale descriptors. So then we defined a new parameter called corrected bulk auroral ionization rate, which then can incorporate this precipitation in the more dynamic precipitation to the model. So here you can see how it looked like along the beams, this corrected auroral ionization rate. And then we can again merge it into with a large-scale particle precipitation model like the ovation prime. You can see that there's different gradients, but everything is very smooth in the ovation prime auroral ionization rates. Here's the corrected auroral ionization rate calculated by the Pfizer, calculated from the Pfizer electron density measurements. And this is how HIME incorporates basically these two different ionization. So when we use this new kind of corrected auroral ionization rates that account for the precipitation, our results show a much better agreement that is shown with the yellow line here versus the electron densities measured by the Pfizer. Here, the purple line shows only the electric field component included, just to show that the difference is basically only due to the description of the electron density. Here you can see a bit of a discrepancy. This is because the cutoff altitude we applied is below 250 kilometers. So above 250 kilometers, it starts converging to the overall profile. And again, there's a lot of things going on with the data, especially at these high altitudes. Our reliability drops to based on the low electron densities. So there are more sophisticated ways to incorporate reliability-based incorporation, basically, or solving this optimization problem that we want to explore. There are also different machine learning efforts for us to understand the dynamic aurora. Here is a recent study by Clausen and Nikish. They have used a supervised deep neural network and they applied it to the TEMIS all-sky imagers. They have basically 6 different categories: the clear sky, moon, or any other light that obstructs the identification, cloudy conditions, diffuse, discrete, and arc type of aurora. They have built a system that could easily be adapted to different to the detection of different mesoscale auroral features, and this enables basically large statistical analysis of aurora databases. Here you can see the Rankin Inlet Geogram at 21st of January. This is basically the central longitude, and you can see its progression through the 9 hours. Here they are showing different probabilities of all different types of aurora in a stacked plot manner. Here you can see the first interval that is identified shows an increase in the detection of auroral arc. And you can see that the image corresponding to this identification shows a faint but arc-type signature. Here you can see that the brown, basically the brown stack plot shows dominates this interval, which is the clear sky conditions. And again, you can see we no longer see the auroral arc a few hours later. It looks more like a clear sky. Here we can see a transition where the discrete aurora becomes one of the discrete and diffuse auroras, basically becomes the dominant probability detected. Here is the first one is the discrete aurora. You can see the time, the image corresponding to this is showing discrete aurora. Here is this is identified as diffuse aurora. Here we can see that the conditions again transgress to the kind of the clear aurora type. So this was a supervised learning algorithm. But basically, what we wanted to do is understand how an unsupervised classification, what it would yield to. This is a work led by my colleague Jeremiah Johnson at University of New Hampshire. And basically, what we started out is looking at the Poker Flat digital all-sky camera images that is located at Poker Flat during the St. Patrick's Day storm, 2015. Here you can see the magnetometer measurements from Poker Flat. We didn't remove the baseline here, but again, this is recently funded, so we're going to do more exploration in this line of work. But you can see basically the magnetic field variations along the day. And this unsupervised learning algorithm applied to all the all-sky camera images from that time yielded to 8 different classes. So you can see that there are these classes are basically overlaps with different intervals of magnetic field variation that we see. For example, when we do not see much variability, like here, we can see the class 1 type of aurora, which probably corresponds to something of a almost clear sky conditions, similar if we were to compare it with the previous data set. But for example, when we have these distinct variations, you can see that the class 4 and class 7 seems to be mostly associated with these rapid variations in the magnetic field horizontal component, where we see these auroral or archetype features. And in class 7, this is basically showing multiple arcs and some almost these kind of wavy signatures. So these help us kind of understand what type of features or classes of aurora we are most likely to see given the magnetic field perturbation. And again, some of the most kind of depressed magnetic field configurations yielded to class 3 aurora, which looks more like a discrete type of aurora. So understanding aurora has various benefits, and it also helps us communicate type of science we do better. One great example of this is AuroraSoros, led by Elizabeth McDonald. And this basically is a tweet-based identification system where people who observe aurora tweets what type of aurora they observed, or it has this pipeline where it looks at the Twitter and tries to pick up tweets that mentions aurora. So people can help either way. Either they can contribute with tweeting auroras that they see, or by identifying the tweets and whether they are really about aurora observed recently, which provides a real-time ability that enables aurora nowcasting merge with the large-scale models that we see. And recently, you might have seen that the Lost Through Auroral Microburst Pulsations rocket LAMP mission, it has been launched, and AuroraSoros organized basically a citizen science campaign event to photograph pulsating aurora during this time to help aid the measurements of the LAMP rocket. Another initiative is the education activities for dynamic aurora studies. This is called Space Weather Underground. Space Weather Underground was initiated at the University of New Hampshire, but recently we have adapted this model to Alaska as well. The program goals are to educate the future STEM workforce, build cost-effective, research-capable magnetometer arrays, and investigate the geomagnetically induced currents. At University of Alaska, we provide 2 different programs. So we have a year-round high school student program where students can volunteer and work every week, dedicated amount of hours to build their magnetometer kits. Or in the summer, we have a 1-week educator development program where we bring high school educators and provide them the magnetometer kits and all the equipment necessary, as well as have classes on space weather and auroral phenomena to basically bring them up to speed so that they can go back and start their own satellite SWAT programs. You can see why it's really important, because here we are showing the science grade magnetometers across Alaska. And remember, Alaska is very big. And you can see basically through the west of Alaska, which is on native land, we do not have any science grade magnetometers. But the green stars show the high schools across Alaska, and this means that at these regions we have the infrastructure, basically electricity and internet, where um, we can start satellite programs and understand the basically the types of aurora we see at these regions better through these magnetic field measurements. The magnetometers we use are simple Aurora monitor magnetometer kits supplied by RIV engineers. You can see its assembly steps here. It's very straightforward. It requires soldering basically and a little bit drilling skills. And in the end, we have extensive deployment and testing available through our student volunteers who lead most of this program. But at the time being, I can say it takes a village. We have a lot of students, their parents invested in this program. And there are two upcoming missions that are going to provide really interesting input for understanding the dynamic aurora. One of them is the EASY mission, the Electrode Jet Zeeman Imaging Explorer mission. It's going to consist of three small satellite missions, three small satellites to measure dynamic auroral electrojets. This is an initiative led by Johns Hopkins University, and the launch is planned in 2024. Its altitude is going to be between 120 and 150 kilometers, and this will investigate source and changes of the electric currents. EASY mission will have a significant outreach and education component, which we are hoping to collaborate on. And the next, the other mission that I want to talk about is the Geospace Dynamics Constellation mission, which will provide, again, unprecedented data for mesoscale studies because of the amount of instruments it has dedicated to measure the ionosphere and thermospheric plasma parameters. This GDC mission aims to resolve local, regional, and global structures, which will help us understand the dynamic aurora much better. So overall, it's a great time to study dynamic aurora. We have various underlying physical processes that lead to dynamic aurora, which hinders our ability to forecast them. But these structures deliver as much energy to the system as the large-scale structures. So it's really important to understand them better. There are new tools like the data assimilation and machine learning techniques that can help advance our understanding of this. And then there are a lot of education and citizen science opportunities to extend these dynamic aurora studies, because this is something that we can directly communicate to a wider public. And then the new missions like GD and EASY will provide, again, unprecedented capabilities to make in situ observations of dynamic aurora. So with that, I want to thank you for your time, and I'm happy to take any questions you might have.
All right, thank you. Does anyone have any questions? You can either raise your hand or type them in the chat and I can read them. Bill, why don't you go ahead?
Yeah, thank you for that seminar, Doga. The data assimilation results you showed were very impressive. They relied on, I guess, on regional or local data from, for example, from Pfizer. And I'm wondering if you've thought about what it would take to do that globally. Like, you know, let's say, for example, assimilate into a global model of some kind.
Thank you for your question, Bill. There are various different ways to do it. For example, we can use multiple radars at the same time, like different super darn radars, but this will require, again, inferring the potential difference at different local regions. So the general problem would be to provide information at each point, which will then, I think, what you're actually asking is to whether we can merge these estimates with a model like assimilative mapping of the ionospheric electrodynamics, like Gang does here. So yeah, that would be very interesting. But again, it's a bit of a resolution issue in between these models to kind of match them.
Okay, thank you.
Thank you.
Another question, Changping, go ahead.
Hi, can you hear me?
Yes.
So about the resolution issue, is there any characteristic spatial or time resolution when we incorporate this HIMI into the GCM model?
So basically, I was thinking of the AMI model, but when we have an empirical model, we can interpolate between any type of uniform grid that we want, which provides us the capability to, for example, downsample the Pfizer electric fields. Running GITM with 0.05-degree resolution would be basically, globally would be too heavy. But like Yuedeng's group, and I think maybe they're not here, but the GITM-R would provide such capability to merge these better. We do not, I do not directly work with US group, but I think they make a lot of progress in that sense because they have this nested grid formation where the resolution can be altered locally. So that would be a more sophisticated way to incorporate some of these electric field estimates.
Mm-hmm. Thank you.
Gong, go ahead.
Yeah. Hi, Doa. Thank you very much for the very interesting seminar. So you mentioned that using machine learning to identify aurora. I have not seen aurora myself that much, but I can imagine that, same aurora, if you look in a different location, they look quite different. So how exactly the general machine learning can help us understand the physics, or even just characterizing? If you look at the one station, you will identify different characteristics from another station, the structure will look quite different. Then, so each, and Aurora is so dynamic. It's just bug in my head is how exactly machine learning can be helpful, especially for understanding physics.
So thank you for the question, Gang. One issue is, for example, we can look at poker flat images, and we are able to extend the possibilities of mesoscale aurora with omega types. Maybe I can share my screen. Sorry. So maybe you're able to see this kind of graph now.
Yeah.
Some of the open questions we have is basically, what are the magnetic field perturbations associated with these type of different omegas? Different type of auroras. So here you can see these are all from the poker flat all-sky camera, and we have a magnetometer located at poker flat research range. So if we can have a larger statistical database of different types of aurora, we can associate the magnetic field perturbation associated with them too. So that will be like one of the immediate understandings that we can have. Again, this would be a statistical understanding, but then we will be able to pick kind of the subset of all of these. Other than that, when we have a database of different type of aurora, and when they are observed, we can have more complementary data sets, like the look at conjunctions and extend this statistical analysis in the way that we can try to infer what type of magnetotail conditions could be leading to those as well.
So how big of the data sets you think would be needed in order to really get something like that, the correlation between magnetometer perturbations and aurora structures?
The size of the database becomes whether we want to have a supervised learning approach or unsupervised learning approach. So for example, if we want to kind of come up with classes, we can just look at a few days of few nights of data. Basically, maybe 1,000 image would be helpful. But if we want to do supervised learning, then again, we have to really identify the evolution and like the whole image. So that would be a quite large data set. But again, other things we can do is kind of look at, again, for the poker flat, the incoherent scatter radar measurements and understand what type of velocity changes associated with all of these type of different auroras are. So I think for each class at their peak, kind of again 100 to 200 images and corresponding data sets would be a good start. Like the initial old data set that I was showing from Clausen and Nikish, I think they had only around a couple of thousand images to come up with this nice database, around 2,000 or so.
Yeah, seems a very daunting task. Good luck with your project.
Thank you. I have a slide that I can show, but one of our, let me show this again. Sorry. So basically, we can also do like a crowdsourcing of identification that can help us do a supervised learning for the Aurora clusters. So we are hoping to launch this website really soon. We have 19 years plus of poker flat data that we can really help crowdsourcing and the community effort to classify.
Yeah, thanks, Doa.
Thank you.
All right, does anyone have any final questions? If not, then thank you again for the excellent presentation.
Thank you.
Thank you.